I just wanted to thank everyone for being here today, and I wanted to quickly introduce our speaker for the next 2 days, the YouTube star, Dr. Andy. Just a little bit about him. Andy got his bachelor's at Carleton College in psychology, and then his PhD in cognitive neuroscience at Indiana University. Following that, he was at Yale at the Haskins Lab for a postdoc, and earlier this year he moved to Ann Arbor to join UMich as a neuroimaging specialist at the Department of Psychology. Apart from that, like we've mentioned in one of the many emails that we sent you, he's the creator of the blog and the YouTube channel called Andy's Brain Blog, which I'm sure has come to your rescue if you've done any kind of imaging before. He also serves as a neuroimaging consultant with multiple labs around the country and travels around the country to do workshops to help imagers like us at all levels. So I just wanted to thank Andy and join me in welcoming him.
Thank you so much. And thank you all for being here. Before we start, I just want to remind again the people in this row, it's a little dark, but there is a cable at about waist height, so just be very, very careful. I don't want anybody getting injured. So we're here today to tour an AFNI, and that's an interesting choice. I think it's a great choice because it's the package that I first started out with, and it has many advantages, in my opinion, over the other available packages, which we'll get to soon. But before we start talking about all of that, I want to give a brief background about how I got to where I am today, how AFNI plays into that, and also an overview of what my role is at the University of Michigan right now. So I started out as a lab manager at Ohio State University, and the package they were using then, at that time, was AFNI, which for me was quite a jump because it has a pretty steep learning curve. It has a reputation for not being that accessible compared to the other ones. But it's a really good introduction, and was a good introduction for me to learn things about coding, about creating scripts, about really having a good, firm understanding about what's going on when you're analyzing your imaging data. Then when I moved to Bloomington, Indiana to do my graduate school work, we started using SPM. So I got introduced to another package, learned some of the trade-offs, some of the advantages, disadvantages of the two, and then lastly, I'm now here at Ann Arbor, Michigan, after a brief postdoc at New Haven. I'm not showing it there, but yeah, so right now I'm at Michigan as part of something called the Neuroimaging Initiative. Just want to say a few words about that. It's a collaboration between all the researchers, anybody who does neuroimaging at Michigan. And I was just talking to Monica beforehand about this position. It's unlike anything that I've really seen before. They reached out to me because this was in the wake of this Eklund paper in 2016. Anybody heard about that? Okay, so it was a paper that called into question some of the methodologies of fMRI analysis. And it was a really big deal. A lot of people didn't know if they were affected by it, and if they were, what were they supposed to do about it? So they got together at Michigan, and they said, well, we have a bunch of these different groups. Wouldn't it be nice if we had a group of people to make some judgments about all these new developments that are constantly occurring, and just to keep people updated on what the best practices are. So that's part of my role, and I work with a few more the technically savvy computer science people who also help out with things like analyzing out the cluster. But it's to do anything such as fMRI analysis, obviously, structural analysis with FreeSurfer is the big one, and more recently diffusion-weighted imaging with programs like TBSS or MRTrix. So if you want to talk to me more about that during some of the breaks, please do. I've only been there a few months. It's very new, but it's an interesting setup, and I don't know if they have something equivalent here at Milwaukee. But yeah, if you want to hear more about it, I'd love to talk about it. Okay, so today, I've been giving workshops for a while now, and only in the past year started to actually travel around different universities. And I've gotten some idea about what's effective, what's not, what seems to work. And the main thing that seems self-evident is that practice is really necessary. We have a very short time frame here. We only have 2 days, as opposed to sometimes they have 1 or 2 week long workshops for these. If you go to say like the AFNI boot camp or the SPM workshop or the FSO workshop, they give you quite a bit more time. So what I really want to emphasize is we are going to, by necessity, be a little bit quicker covering certain concepts. But I do want to give you some templates you can use so that if you need to practice it outside of this, you'll have enough of a background to make some educated choices about what to do. Basically, if you don't use it, you lose it. Another thing is, neuroimaging is constantly evolving, and AFNI's been around for a long time. It's still being supported. They have a great group of people who are maintaining it, responding to questions, keeping up with all the updates. But besides AFNI, there are a lot of different packages that come up. Things for analyses like MVPA, for connectivity, and it's really hard to develop a good sense of what has staying power, what's going to be around. What happens sometimes is people will learn a package or they'll learn a toolbox, and it seems to be supported for a year or two, but then the people who developed it, they move on, and if you spend a long time learning it, it can sometimes be seen as wasted time. So this is kind of a hard skill to develop, but as long as you get a good foundation of what the concepts are behind these different packages, you can be a little bit more flexible for whatever tends to come up and whatever new methods come around. And lastly, as I hope I'll be demonstrating here, animations are very useful to learn concepts. Whenever I've read papers explaining some new technique or some new concept, usually they have panel 1, then panel 2, maybe panel 3, and it's up to the reader to mentally fill in the links about what's going on when certain processes are happening. And wouldn't it be convenient if you saw some kind of animation showing in real time what actually happens? So part of what's guided my teaching philosophy lately is to try to make those links explicit, to kind of guide the reader, guide the viewer into what's actually going on. So I hope that will be useful today. It's something I've been working on, especially in the past couple of years, focusing kind of on production values, for lack of a better word. So we'll see how effective it is today. Okay, so I'm going to break out for a second and give a brief overview of the website. Let's see. Yeah. So if you don't have the link, so this is my website right here, amysbrainblog.com. If you go to workshops and then click on Milwaukee, this has a detailed annotated agenda about what we'll be doing over the next 2 days. Just so you know, this is a relatively new website. The old one was Blogspot, but I tried to upgrade it. Okay. So you can either type this in or just andysbrainblog.com, click on workshops, then click on Milwaukee right here. So there are a few things here. I mean, most of this has been uploaded onto the computers, downloaded onto the computers. And before we start with the first practical, we'll give you instructions about making sure that you're in the right directory to start doing what we're doing today. But I just want to give a really brief overview of everything. So day 1 is the fMRI fundamentals, conceptually, and also an introduction to AFNI. What sets AFNI apart from the other packages? Very brief review of how we get fMRI data. We'll then go on to our first practical session where you'll be doing some hands-on pre-processing We'll be going through each pre-processing step. Why do we do it? What are some choices you have over certain parameters, and why you might decide to use them. Using the AFNI GUI, it's loads of fun. Take a lunch break. First level analysis, group level analysis, and then day 2 is wrapping up a lot of what we do with fMRI analysis, which is getting to something called region of interest analysis. And for a lot of people, say, at least the majority of studies I see, region of interest analysis is usually the end goal, right? So you run your model, you pre-process everything, you have some sort of experimental design set up, and then you extract data from these regions to try to test for things like regional specificity, double dissociations, or you extract it and you use that data in some kind of model in some other package outside of AFNI. Right? So for most people, once you get up through this and you're able to do ROI analysis, you're fluent in it, you're basically set for a lot of the analyses you're going to be doing in fMRI. I'll be giving a brief lecture on graph theory. There's no practical. Just kind of getting you introduced to the basics. And just to let you know, in a few weeks I'll be giving a workshop on the Con Toolbox at UMass Amherst. You don't necessarily need to go out there. I'm not going to stop you. But I mean, you could register. That I don't think that they would turn you away. Last time I was there, they had a pretty big space. But I will be recording that and uploading it. And on that point, I'm also recording everything that we're doing right now. So it's a screen capture. It's just recording everything that you're seeing up on this slide projector. I'm also recording everything through the microphone here. So be very careful about what you say, because it will get picked up. You know, I can edit it out if there's like something like totally crazy that happens, but I just want to point that out. I don't want to kill the informality of it, but just be aware, just by necessity, it will record everything that gets said. I don't know. I haven't had any problems, but I just want to throw that warning out there because you never know. I was at I'm not going to name names, but there was a job talk back in Indiana many years back, but they record all their job talks, right? And there was this one person on the search committee who wanted to ask a question, and effectively he got ignored and then he had to move on, and he said some stuff and it was all being recorded. So just be aware of that. You can ask me during the break all about that. And then we'll be wrapping up with an introduction to multivariate or multivoxel pattern analysis. This is going to be kind of a capstone exercise because we're going to be analyzing this Haxby data set from 2001, like this original MVPA data set. And I don't have a pre-processed folder with all the MVPA stuff. We're basically going to be walking through talking about, okay, how should we do this pre-processing step? You'll kind of be helping me. I'll be demonstrating it up here. And then, what kind of ROI are we going to choose? Because we'll learn about different options that we have. You could do it from NeuroSynth. You could do it from an atlas. You could do it from coordinates from another study. Basically, we'll see how that goes. This is kind of a new thing I want to test out. And then with the time afterwards, you can use that to analyze the other subjects in that directory. So we'll see how that goes. That'll be it. Any questions about this agenda as you're looking over it? Okay. Again, by necessity, I can't get too specific on things like, for example, MR physics. I'll have a slide or two. We're not going to go in depth. Things like FIR analysis, if you've heard of that, we're just not going to cover it because we don't have time, and it's not that relevant to this specific data set that we're using. Those things are important, but certain things will get left out. Okay. Back to the slideshow. Okay. So I talked about a few of the things we're going to talk about a few words about AFNI. Very, very interesting package. Actually developed initially back in the mid-90s at the Medical College of Wisconsin. If you didn't know about that, yeah. Bob Cox, who is currently at the NIH and has been there for a long time, started out as, should I say researcher, but he worked at the Medical College of Wisconsin and he developed AFNI kind of in response to some demands that other people had there. And as you'll see, the graphical user interface looks like it was developed in the 90s because it was, and it hasn't really had a makeover since then, but it still does everything that it needs to. And I'm sure that as you use it, you'll come to love it. You know, it has a certain charm, as you'll see. A lot of jokes that they will output. By the way, just to take a brief poll, who has used AFNI before? Okay. Who's new to Unix, the command line? New being like in the past month you just started using it. Okay, so a fair amount. All right. Yeah. AFNI does have a relatively steep learning curve. You do need to have some fluency with the command line to use it. Just to let you know. A lot of the things that I'll be typing out, it shouldn't be too complex. I'll be using mostly, CD, ls, running shell scripts with tcsh. That's kind of the extent of it. And then when we talk about scripting, I'll talk about loops, just so how you can save a lot of time. But just be aware. I mean, if you're really new to Unix, once in a while I might do a command and it may not make a whole lot of sense. Feel free to stop and ask me, some more details about that. I'll try to be as clear about it as possible. But for the most part, if you know the basics, and I heard that you did take some kind of refresher course recently, you should know enough to follow along with the basics of what we're doing. The last thing I like about AFNI is, I always like having people learn how to make educated choices about what they do. You like that? Okay. Yeah, people talk about black boxes and it's how they're so bad. SPM is kind of a classic example because it has a pretty nice graphical user interface, but you don't tend to see a lot of what's going on under the hood. AFNI almost has the opposite problem where you have too many options and it can become quickly confusing about what to do. But I prefer more that because you really do have to understand what goes on each processing step and what the output should look like after each step, which is why I really like it. Okay. The data we'll be using for our practical sessions is downloaded from openneuro.org. It's a very, very good website. Like it a lot. It's an open access repository of different neuroimaging data sets. They have a couple of classic ones. They have the Haxby data set for one. They have a few others, and people are uploading new things all the time. Now, they're in something called BIDS format, which is convenient because it makes sure it's a kind of a standardized format in terms of the way that your data is structured, how your timing files are structured, which is good because the scripts that we use today, if you have enough of a Unix background, you can just do some slight alterations and then apply it to another data set. So if there's some other data set that's more interesting than the one that we're using today, there are lots of them out there, something related to social neuroscience or decision making, anything like that, you should, in theory, be able to make some small changes and apply it to those. The data set we'll be using today is the flanker task. Not very complicated, very well-known effect. For those of you who don't know, the flanker task, it's like these chevrons going in a certain direction. Let's just say arrows going in one direction, right? And then in the center, there might be one arrow that's going in the same direction as the flanking arrows or in the opposite direction. And the theory is, okay, if I have to press right button to say that the center arrow is going right or left that says it's going left, If it's flanked by congruent or the same direction arrows, that's a lot easier to do. You're a lot quicker, you're a lot more accurate than if the flanker arrows are in a different direction. That's it. It's a very, very simple task. And we know that there's a very strong behavioral effect. People are slower in the incongruent compared to the congruent condition. And we also have this very reliable activation in the medial prefrontal cortex. So the reason I use this admittedly simple data set is because it'll allow us to cover all the concepts of fMRI analysis, pre-processing, building a model, and at the end of the day, we know what we should get. So it's very clear if we screwed up. Right? But even with this simple data set, there's a lot of stuff we can do in terms of ROI analysis, testing for double dissociations, doing a few different things. Okay, so now for the review of fMRI. And feel free to keep eating if you need to keep eating, because it's just me talking for the next half hour or so. So all the principles of magnetic resonance imaging, what used to be called nuclear magnetic resonance before they changed it because of PR purposes. Nuclear had some connotations that people didn't like, so they changed it to MRI. But the principles about how magnetic fields affected something called the spin of protons within different pieces of matter was pretty well documented. But it wasn't until the early 1990s that they started to use it to do functional imaging. So before then, in the 70s, the 80s, MRI was popular for diagnosing things like tumors, especially in the major organs like the brain, the pancreas, the liver, and so on. Now, up until the early 1990s, the dominant functional imaging method was called PET, or positron emission tomography. Has anybody ever had a PET scan? I'm just curious. Okay. They're getting more and more rare for a few reasons. One is, to do a PET scan, you need to inject the subject with a radioactive tracer, which not everybody is cool with, because this thing binds to glucose, which can pass through the blood-brain barrier and is then used by neurons in your brain. Right? So you can't have too many PET scans in a year, for obvious reasons, but it's very useful because it gives you a direct measure of what parts of the brain are using that glucose. As you'll see, compared to fMRI, fMRI is a few steps removed from actual neural activity, but PET is more or less, it's a little bit closer to the actual underlying neural activity without actually opening up the brain and having to do single cell recordings. Now, what you'll see with the typical PET scan, here's a typical one, is you see activation. It's pretty clear where it is, but your spatial specificity is very low. So you can see a pretty big region of the brain implicated in whatever process that you're looking at, but it's very hard to see anything very fine-grained. Now, as MRI technology became more refined, as MRI became more and more widespread, they started to look into some of its capabilities. And one of the insights was that, well, most of the body and a lot of the brain is composed of water, right? Something like, I don't know, I see different numbers, like 80-90% of the brain is water, it's a lot. A lot of the brain is water. And water, as we know, is composed of hydrogen and oxygen. So, if we can be sensitized to what's happening with hydrogen when it's under the effects of magnetic resonance, we would be able to gain quite a bit of signal if we tried to measure it. Now, the key insight here was that if there is hydrogen in the neighborhood of deoxygenated blood, you get lower signal when you try to measure from that same area. But if the blood is oxygenated, you get higher signal because just by the magnetic properties, oxygenated blood perturbs the magnetic field less than deoxygenated blood. And this whole phenomenon was called the blood oxygenation level dependent signal, or BOLD signal. One of my colleagues in Michigan, John Janitas, said that because this is actually a measure more sensitive to deoxygenated blood, it should be called the blood deoxygenation level dependent signal. But you can't say BDOLD or something, so BOLD was the one that stuck. And the person who first had this insight, and he may win a Nobel Prize for it at some point, was Ken Kwong, who at the time, I believe, was working at MGH, Massachusetts General Hospital. And he made this key discovery. Right? So he was looking, I think, in rats or mice at the first time. And he had a couple of slides showing very clearly that if you had the rats breathe 100% oxygen, you got a lot more signal than if they breathe some mixture of oxygen and CO2. Now, what we can do with that and how this is going to relate to building our models is if we have conditions such as a flashing checkerboard, which is what they used to do way back in the day, to measure visual cortex activation, you can have periods where you're just showing this visual checkerboard, right? It's very clear. We know that that should lead to higher activation in the visual cortex. You contrast that, and this is the key part, you contrast that with periods of baseline, or when it's off, or some control condition. You take the difference of the two, and I think at the bottom, yeah, this is the contrast between the two. So let's see what that looks like in real time. This was the first video that they made of it. So there's the front of the brain, this is the back of the brain, visual cortex. Here's what the visual checkerboard's on. Now it's off. And after a little bit, it goes on again. And this seems almost trivial right now, but this was a huge landmark study because it showed non-invasively in humans you can take a contrast in BOLD signal between two or more conditions. And once you can do that, you can apply this to virtually any kind of design, any kind of stimuli, and examine different parts of the brain, and subcortical regions as well. It's a simple design. It's called a block design. It gives you the most statistical power. As we move on, we'll talk about other designs like event-related, mixed designs, but that was the original one. And it's too bad that we're alive when we are, because back then you could do something like flashing checkerboard and you get a science paper with like 6 subjects, right? Auditory with like 6 subjects. You get the auditory cortex. Wow. You get published in a really high profile journal. So those were pretty, they seem trivial to us, but this was the first functional mapping of the human brain. So it was a big deal. So just to give a brief summary of what happens in a typical fMRI experiment. First, there's some kind of stimulus like that. It gets transduced into neural firing. Right? So any neurons that are sensitive to that particular stimulus or cognitive condition that you're presenting are going to fire. Theoretically, that should happen. And if there's more neural firing, there's more oxygen consumption. Because as we know from these neurons firing, it needs oxygen to restore these gradients, this sodium-potassium pump, that it needs to maintain a constant certain polarization. When there's more oxygen consumption, through processes which are still being investigated, something called hemodynamic coupling, there's more blood flow. Somehow it sends a signal that there needs to be more blood in this specific area, and the blood's going to be carrying oxygen. And if there's more blood flow with oxygen, there's greater measured signal from that area. So this is perfectly logical, right? It's a pretty simple chain of events. But what you'll notice is that the observed signal that we're seeing down here is quite a few steps removed from the actual neural activity that we're assuming at the very beginning. if you do any reading into this, and this is a whole different literature, how much is the actual signal affected by the neural firing as opposed to, is it just some artifacts from nearby veins that are draining? Like we're still trying to figure out exactly what the whole interaction is going on there. But for most purposes, it does seem to hold up pretty well, especially when they did some combined studies where they did actual single cell recordings, local field potentials, and things like visual cortex, auditory cortex, and also measured the hemodynamic response. And they do seem related. So there's some evidence to suggest that, yeah, this is, whatever we're measuring here does seem to be affected by the neural firing. That seems to be logical. But just keep in mind it is several steps removed, and we do need to interpret it accordingly. Okay, so we made a bunch of assumptions, so let's make a few more assumptions. Why not? Once we're down that hole, why not just keep going? The second assumption is what this bold response actually looks like. So if I give you a stimulus like that, here is what that bold response is going to look like unfolded over time. So this is the signal that we're measuring from the scanner right after like a theoretical punctate or instantaneous event. Right? Could be a stimulus presented like for so brief a period we essentially characterize it as an instantaneous event. But it unfolds over time. It's called sluggish. It's called slow because compared to things like single cell recordings, compared to EEG, this is a couple of orders of magnitude slower than that, right? EEG single cell recordings are talking about milliseconds. Here we're talking about 10 or more seconds for this whole thing to unfold. You'll notice it takes some time for it to start to rise. It peaks around, they say, 4 to 6 seconds, and then it starts to taper off. And also, in some cases, you see this undershoot that goes on for several seconds longer. Now, one thing you should know is that we can model this thing mathematically. This bold response is modeled by something called a gamma function, where it's bounded on the left by 0, it raises up, and then it has a longer taper to the right. What we're going to be doing when we start estimating our models, doing all the pre-processing, we're basically trying to find out how much we need to modulate the amplitude of that bold signal to best match our data. And this entire function, we're going to call this a basis function or the hemodynamic response function, because this is a stereotypical pattern that we usually see in response to a single stimulus. But what you should also know is this thing was derived from these early studies examining mostly visual cortex and primary somatosensory cortex. So it's a very good model of what's happening in those specific regions, but is it the best model of what's happening in, say, prefrontal cortex or subcortical areas? Maybe. Probably not. Maybe it's pretty good, but it probably doesn't look exactly like this. Nevertheless, we often use it because it's the best thing that we have. It's simple to use. We're estimating a single parameter, and it makes all of our computations a lot easier. You could do something more complicated. You could try to make your own. You could try to, by subject, try to derive what seems to be their idiosyncratic bold response and use that as a basis function. That's all open to you. But for the purposes of what we're doing today and for what most people do, they just use this HRF. Now, let's say that we had multiple bold responses, which is typical in a usual experiment. We have many, many different conditions, and these days we have them very close together in time, relatively speaking. So if we have response 1, and then another response right here, and another response over here, in blue is the total signal from all 3 of those distinct events. The first one was modeled in black, the second one in red, and the third one in green. So notice the actual signal we're going to be getting out of the scanner is in this blue, right? It's going to look pretty messy, pretty complicated. Add some noise on top of that, add even more events that are overlapping, you get a very, very messy signal. Okay, so remember this, fMRI data is mostly crap. It just is. It's super messy. There's physiological noise, there's scanner noise, the subjects move, the subjects breathe. Basically, the subjects show signs of life, which is very inconvenient because it messes everything up. The bold signal is not always reliable. It's in these, we're looking at a bunch of different places. There's things like spatial correlation, temporal correlation. It's crazy. So we need a lot of trials to just get a good grasp of what's going on for a single condition. But what we know about all these different bold responses, we can decompose this more complex signal into the individual bold signal for each condition. We call this deconvolution. When all these things get mixed together, generate this more complicated signal, that's called convolution. Deconvolution is trying to untangle it and bring it back to these individual responses. So that's an assumption. Let's make a couple more, right? The next one is something called linearity. Very important assumption because if we didn't have it, we wouldn't really be able to use the general linear model, but thankfully we can. Linearity assumes that if we have 3 overlapping responses, right, and we decompose them into their constituent single responses, we should be able to recover those individual responses. And importantly, if we added them all together, they should sum roughly linearly, right? So trial 1, 2 trials, 3 trials tends to scale in a linear manner. Obviously, this breaks down at a certain limit, right? But we're working within certain parameters where we don't think we'll ever reach that limit. It's like, okay, percent signal change, it goes up, let's say, I don't know, 2 or something for 1, 4 something, 6. If we kept stacking those up, what do we get? Like so much blood that the brain explodes? No, it saturates at some point, right? There's an image for you. But for most practical purposes, everything that we do, we assume that it's roughly linear. Okay, it's not perfect by any means, but it's a pretty good estimate. And if we can make that assumption, it makes all of our subsequent calculations a lot easier to do. So we just assume it. So we're not going to press on this too much. Like we found this, and we're like, okay, let's just stop, and let's not do anything beyond that. I'm kind of joking. I mean, there are some calls for doing things like trying to model some of the nonlinearities. I haven't done it. It's beyond the scope of this. But obviously, if you could do it effectively and efficiently, it might be a better model of what's going on. But we're not going to do that because it's hard. Okay. Go over a few of the designs and then tell you which design we're going to be using for the data we're looking at today. First one from that original Kwong experiment in 1992 is called a block design. So called because the trials that you have come in large blocks, right? So we have, let's call this condition 1, condition 2. We have, this is all condition 1, right? So we could have a ton of trials in here, but they're usually spaced closer together. We don't necessarily care about any individual trial. We just want some kind of response to just the fact that they're being exposed to that particular stimulus or a cognitive state. Same thing for condition 2, and then we go back to condition 1, condition 2, so on and so forth. Now, if you do that, okay, obviously you can't get a good sense of what's happening at individual trials. But statistically, it's extremely powerful and it's easy to design. You're not going to run into this thing called collinearity, which we'll talk about in a little bit. It avoids that whole problem, so that's nice. And also, if you can get the subject to do it, and it's not confounded with anything, that gives you really, really high statistical power. The disadvantages is that it is boring. Okay, so if you're trying to do this, anything outside of something like a basic somatosensory task, say flashing the visual checkerboard, having them hear some kind of auditory response, it's really not that engaging to do. It can be predictable, especially if there's a pretty consistent off on or A B, and also if you want to do anything more complex, like have some kind of complicated interleaving of conditions, it doesn't really lend itself to that. Which is too bad, because most of what we're doing these days, by necessity, needs a more complex design. Right? We have a lot more conditions. We have irregular timings to keep the subjects more engaged. So event-related designs is, I would say, the majority of what's being used these days. So a couple of different ways you can do it. There's something called slow event-related design. You may not be able to see some of the font here, but what's happening is each color is a different condition. Right? So we have 2 trials of condition yellow, 2 trials of condition red, 2 trials of condition green. And so, when we look at these HRFs individually and we look at them summed together, they're spaced far enough apart in time where we can see the individual bold response to each individual trial, which may be of use to you. But this could be too unwieldy, it could take too long, right? Especially if we want to get a lot of trials, which, as I showed you before, you need a lot of trials if you want the power to estimate what the bold response looks like to a typical condition. So we tend to space them a little bit closer together and also make them more irregular. Okay, this is called jitter. And it's necessary if you have overlapping HRFs to have jitters so that deconvolution can occur. So notice that we have the individual HRFs. This is, say, theoretically what they actually look like. But if we look at the actual signal that we get from the scanner, it's going to look more complex and more convoluted. Involved. Yep. But because we have these assumptions of linearity in particular, we can decompose this back into the original HRFs for each condition. Okay. Any questions so far on that? I'm giving a pretty fast overview of all this different fMRI stuff. Conditions, experimental design, physics. Okay. We got a soundtrack in the background. This is interesting. We must be in the dance department, yeah? Okay. Or art or something. Yeah. Sounds good. All right. Advantages is the converse of what we saw with block design. So this is more engaging because it's a little bit more, say, unpredictable. Yeah, you don't necessarily know what's coming up, so you can't fall into like a really predictable groove. And also, you can use more complex designs. Obviously, no, because we don't have as many. We couldn't just like cram as many trials as we could into the block design, and because they're not so cleanly separable, it's going to have some less power and also be susceptible to something called collinearity. I'm not going to get too much into this, but this is a design consideration for when you're making your own experiment. So like I said, collinearity is when there's not unique solution to decomposing this more complex signal into individual HRFs. And one thing that can cause collinearity is if you have overlapping HRFs and they're at a consistent offset from each other. So I have condition A and condition B is always 2 seconds or 4 seconds or what have you after condition A. So you'll get this overlapping more complex signal but you're basically running into a situation where there are infinite solutions to what the individual HRFs could be to create that more complex signal. So if you space them out, you're basically sampling along more parts of what these two combinations could be to lead to this more complex signal. If you can do that, then you can get a better estimate of what the individual HRFs are. Some software you can use, there's OptSeq2, OptSeq2. Has anybody used that to design a study? It's pretty old, and I don't know if it's being supported anymore. But that being said, I think it still does pretty much work. Basically it makes sure that you don't get collinearity, and it tries to optimize your design given the number of trials, number of conditions, number of time points. So that's something you may want to look into on your own. I haven't found it that easy to use. It's a little opaque what some conditions do, but that's there for you to use if you want. Okay. So the actual data set, like I said, the flanker tasks. This taps into something called cognitive control or executive function. The way I'm going to define it is filtering out irrelevant stimuli to perform a task. I got really embarrassed teaching about cognitive control in an intro psych class because I used this crazy example where I said, imagine you're at your friend's house and their phone rings. And you have to say, okay, I'm not in my house, so I'm not going to answer it because I'm in a different context, right? So I get the stimulus, a phone rings, I'm not going to pick it up. And they're like, what do you mean your friend's phone? I'm like, oh, like the ones that are like on the wall. And they're like, I'm like, okay, I'm way too old to teach this thing. You guys remember that, right?
Yeah.
Good old days. This is a schematic of that flanker task I was talking about before. So these flankers, they're like arrows, right? So this is congruent. They're all going in the same direction. And I'm sorry about this. They can all be going in the same direction. They're congruent in that case. So if they're instructed, just pay attention to the center arrow, respond to that one, left to right. That's very easy to do. If it's incongruent, say the flanker arrows are going right, center arrows going left, that's a little bit more difficult to do. Okay. Not complicated, but you get a very reliable effect. And we're going to look at it. Two conditions, really not too complicated. Let's see here. It's a brief video just giving you an overview of what we actually downloaded in case you were curious. So this is openneuro.org. This is the flanker task data set. And it's in something called bits format. So everything is formatted in a standardized way. So you get some information about what goes on in it. Within each subject directory, there's an anatomical directory, there's a functional directory, and if they had diffusion data, there'd be a diffusion directory. Pretty simple. Within the functional data sets, they have each functional run and then an associated events file. I don't know if you can read that, but there's the actual neuroimaging data, there's the events file. And within that, we have information about the onset in seconds from the beginning of the scan when a certain trial of a certain condition occurred. So there's incongruent, congruent. There's also information about whether they made a correct or incorrect response. From what I've seen, they're basically almost at ceiling, so I'm just collapsing all incongruent, all congruent. Now, if you're running your own experiments, okay, I'm being a little sloppy, a little lazy, you would want to model any incorrect trials, right? Because presumably they would have some maybe different neural response to that particular condition. Today I'm keeping it super simple. I'm collapsing because they're like at 95% accuracy or better. So, probably throwing in a little bit of noise there, but I think it pretty much washes out. Okay. Now, this gives us the bare minimum we need to do an fMRI experiment. We have an anatomical data set, we have the functional data, we have the timings for what happened when. So we're going to be creating something called a model, which is going to look like that more complex overlap of those conditions I was showing you before. So you put, if your timing was here for condition 1, it's going to raise up there. Condition 2 here, you see the HRF, condition 3, and so on. We're going to deconvolve that complicated signal into individual bold responses for each condition. Okay, now just to illustrate conceptually what this data looks like, because it's not immediately intuitive just looking at it on the command line or the GUI. I like to think of each volume as like a big Rubik's Cube, right? So we image the entire brain, but each smaller cube is something called a voxel. That's the smallest spatial resolution element that we have, and we get signal from each of those. So we take an entire snapshot of the brain, time point 1, another snapshot, time point 2, another snapshot, time point 3, and with the functional data set, we're just daisy chaining all of these different volumes together. So we have 3 dimensions and then a time dimension in the 4th dimension. Now, if you zoom in on all these different voxels, remember it's our smallest spatial resolution element. They contain a different number, right? So in this voxel, it's 0.75, over here 1.25. That is, at that particular time point, what the signal was in that voxel. So you'll see these things called time series later on, very important, which shows how the numbers in each of those voxels varies over time. So this is a conceptual thing that I got hung up on when I first started. I'm just trying to make it clear. We're measuring this signal in each voxel separately, right? And then we're fitting the model at each voxel separately. So as long as you can keep that in mind, I think it'll make the rest of what we're talking about a little bit clearer. Yeah. Okay, so the pre-processing steps. We'll get more into this in the practical in the next part. Here are the typical ones. We'll come back to this. First, we determine whether we're going to remove the initial TRs. There's something called a saturation effect specific to these scanners. We then extract the skull through skull stripping, brain extraction, slice timing correction, motion correction. Those are both to correct for different onsets of slices being acquired, and also if they moved at any time during the scan. We register the functional and the anatomical together so they're in the same space. Then we normalize them to a template space which has standardized voxel dimensions. And then we smooth. Okay. That's to average over signal over a neighborhood of voxels. And in the second lecture, before we do the actual practical, I'll show you some animations showing exactly what each of these things are doing. But just be aware of that. I covered most of this, just the advantages of the AFNI package. The main thing is it's fast. It's very, very quick compared to FSL or SPM. I don't know how they do it, but it's just very, very quick. And I really like it because if I need to rerun something, it's not really a chore to do that. It's customizable. This can almost be a problem. Back when I first started using AFNI in 2008, reading the message boards was totally crazy. It was like the Wild West because everybody had their own script about how they wanted to analyze the data. Does anybody remember those times? Okay, this is, yeah, who said? Yeah, okay. Yeah. So it was nearly impossible to debug things because, people would, not that this is bad, but they would read the textbook and say, okay, so I got to do this, I got to do this, got to do this, look up what command does that, put that in my script, and then just run the whole thing. It's usually not that simple. Now, they've changed that in recent years. They use something called these Uber scripts to generate standardized processing streams. So you select certain parameters, you still have some control, but the actual script that gets generated is from this higher level program. Some people don't like it. I think it's for the best, and we'll see that in a little bit. The last thing is their support, which is really great. The world famous AFNI message board. Okay, it's only about neuroimaging analysis, so there's no like other category that you can like talk about politics or sports, unfortunately. But they're very, very good about getting back to people very quickly. Okay. Again, this may be a little small to look at, but you know, I took the snapshot a few days ago. I think on September 26th, and all the replies are like 25th, 26th, 27th or so. That's very, very good. Now, later on, I'll be giving a demonstration of the Uber command interface. Unfortunately, we were not able to get that running on your machines, so you're not going to be able to do this particular thing. Sorry about that, but you will still have the output from this to still run. So basically, you know, you can go back, look at this when I'm giving the demo just to get a sense of how to use this. Not complicated to use. It's very intuitive. You just fill in the different fields, you change some parameters, and then you run it. So pretty simple. It's a pretty cool interface. And again, I think it's for the best. Now, disadvantages. There is a very steep learning curve, especially if you don't have a computer science background. Unfortunately, you know, if you have more of a psychology, cognitive background, neuroscience background, it's a little bit harder to learn AFNI than if you had the converse where you had a really strong computer science background and then you were trying to learn how to do the fMRI analysis. That's just been my personal experience looking at the people who have a really strong coding and computer science background. There are also some confusing terms. Some of these are legacy, so you'll see things like O'Regan TLRC extensions. It's like, what do those mean? I'll walk you through that. Can't cover every possible thing that might trip you up, but it's old, you know? It's been around for a long time. It was developed back in the 90s. And they've had to keep some things for compatibility purposes, which when you're doing your analysis may not totally make sense. So just bear with me. And then the GUI's old. It's an airplane cockpit, right? I mean, we're going to get up close and personal in a couple hours with AFNI GUI. Humor is a double-edged sword because they tell a lot of jokes in AFNI. If you've used it, like when you sign off, they'll have some kind of a valedictory or joke or something, or like the screen will melt down if you close out of it. The first time it happened, I freaked out. Some people hate it. I think it's kind of endearing. That's just their style, okay? I can't do anything about it. You can also upload your picture if you want to make yourself like an AFNI user, and when it loads, it shows like a random source image. So if you don't like it, you should probably leave now. It's not going to get any better. I'm sorry. Okay, I want to end this with a couple related topics. So we're going to do a brief demo converting DICOM data to NIFTI data. So you'll have this in the recording. During one of the breaks, if you want to download this thing called MRI Crow GL, you're free to, and I'm happy to walk you through that. That wasn't mine, was it? Okay. All right. The reason I want to cover this is because raw data from the scanner is usually in DICOM. What kind of scanners do they use here at GE? Okay. Okay. I know that in Siemens it's in DICOM format when it comes off. Is it same? Is it same in GE? Okay. Good to know. Good to know. All right. So this is a very, very useful tool. MRI Crow GL, it's for visualization, but also it has this conversion tool built in. So it's a suite of programs, and it can do a few other things as well. I don't use it for anything too complicated. It does have a command line version, which is useful if you want to script things from start to finish, from the very raw data up through everything that's been processed. But I'll show it through the GUI. Okay. Again, we're just going to capture this. It's not too complicated. Download the exercise data set. Yes, please. Come on, Squarespace. While that's waiting, I'm going to open up MRI Crow GL. Okay, that's what it looks like just when you open it up. You can render your results on there. You can slice the brain in different ways if you want to. Here's this DICOM to NIFTI. So these DICOM files, you get one, I think, is it per volume? Per slice? Yeah, okay. Yeah, so this is the raw data that you'll be dealing with. It's useful if you want to look at some parameters that you can't see typically with something like AFNI or SPM or FSL. There's certain header information that usually gets erased by MRI Crow GL, so like personally identifying information, but there's also some information about the scanner, which in some cases you may want to know about. But just to show you how easy this is a pretty simple tool to use. So aside from the visualization part of it, you'll notice that they have this import option up here. You click on Convert DICOM to NIFTI. I have no idea what Convert Foreign to NIFTI is. That must be fun. And then it will output them in a certain format. Right? So if you hover over this, you can see what the different options are. It's using this string formatting procedure, which may be new to you, but basically if there's an ampersand or percentage sign and a letter, it replaces that with a variable, with some field. Sorry, I used the wrong one. DICOM to NIFTI test. Open it up, converts pretty quickly. And then if you look within there, we have this NIFTI file, which I could then open up in the AFNI viewer, use it for pre-processing, and so on. So again, super quick. If I had a full data set, it would take a little bit longer, but not much. It's a very quick tool. Notice also that they have this formatted with bids if you want to. Right? So if you want to convert things and have it be BIDS compatible, either for uploading to OpenNeuro or to use some of the OpenNeuro tools, you can do that as well. Okay, so just so you have that. And then the last thing for as part of our introduction, I think we're still on time here. By the way, last week I updated the schedule. In case you'd looked at it a lot earlier. I blocked an hour 15 for the intro, an hour 15 for the practical coming afterwards. Okay, now I had some people request, me to talk a little bit about power and fMRI studies. This is a touchy topic, especially with this so-called replication or reproducibility crisis. And power, so I'm going to define it, is if the effect exists that you're trying to detect, how many subjects would you need to detect it 80% of the time? So in other words, we have a null distribution centered around some null value. And let's say I'm assuming that my true effect is right here. So my alternative distribution is centered around where I think my effect should be. Now, if this represents my cutoff, alpha 0.05 for the null distribution, and how many subjects do I need to make this distribution in such a shape so that 80% of the time I would detect it? Right? So there's always a chance that this effect exists, but I simply fail to detect it. That's totally reasonable. But we're assuming that my effect is of a certain magnitude, and also, as we know, the variance of these distributions changes as a result of how many subjects you have. So how many subjects do I need so that I squeeze enough of this distribution past this alpha threshold so that 80% of the time I would successfully detect my effect. Say that it's there when it truly is there. Now, 80%, how did we get this number? I don't know. I don't know how we got p less than 0.05. They just seem like reasonable numbers, right? I've helped write, and I've also read a few grants in my day. Isn't it curious how many grant submissions have 80% power for the effect that they're proposing to detect? I'm not saying that there's anything underhanded going on, but it seems as though when we are, say, looking at other studies to make some sort of guess for our power estimate, we may be looking at effects that are inflated. I'll be covering this in more detail tomorrow when we talk about ROI concepts, because all of this is interrelated. Okay. Not trying to get people too down or anything, but a lot of these effects are really hard to detect. They really are. So you need a really strong effect, and you need a lot of subjects. And it's usually more subjects than people are willing to scan. I'll show you why. The power for something like a one-sample t-test, the most basic test that you would do with some of your imaging data. Let me show you what these power curves look like. So we can model these curves as a function of how many subjects you have, right? And also what the true effect is. So let's say that the true effect size is 0.2, or 0.5, or 0.7. Let's start with 0.2. If I want 80% power, and my effect size is 2 over here, I would need 200 some subjects to reach 80% power, right? So are you looking at a percent signal change of 0.2 or less? You're going to need a ton of subjects. Now, this doesn't tell the whole story. I mean, there's other things we can do, like ROI analyses, other ways that we can try to really, restrict our analysis, make the power a little bit stronger, and that's totally legitimate if you have a good reason for doing so. But this is a general case, and it should worry some people. So even a pretty strong effect of 0.5, or I'll say 0.5, 0.8, it's going to cross at about 40-ish, right? So it's a pretty strong effect in the fMRI world. So if you're thinking you're going to detect something like that, got to be aware, and even for a very simple test like this, to say nothing of individual differences or interactions, you're going to need a lot of subjects. Looking at correlations, okay, so again, we can also interpret correlations as basically effect sizes. This is not going to work if you have a correlation of 0.1 or less, right? Even a correlation of 0.3, let's take a look at that, 0.8, 80 plus for a correlation of 0.3. Yeah. And 0.3, I haven't done a lot of correlation analyses, but that doesn't seem too unreasonable. Do a lot of people here do individual differences or anything of that nature? Can maybe speak to that? Okay. Again, I'm not trying to get you down too much, but it's just a fact of life. Now, how do you do a power analysis for an fMRI analysis? Couple options. The first one, so there's fMRI power. I actually saw Jeanette just last month. Sala and I saw her, right? Mm-hmm. But she doesn't maintain this anymore, from what I understand. So I used this maybe 5-6 years ago. It was useful, but I don't think it works with newer versions of MATLAB or SPM or FSO. I think it was a MATLAB-based tool. So, one, if you don't have MATLAB, you can't really use it. 2, it needs to be in SPM or FSL format. The newer option, which I'd recommend, is something called NeuroPower Tools. It's all online. very useful. You just upload your data or you get it from some other website, and it will generate power curves, which you can look at later. Okay, so here's a brief screencast I made about how to use it. So they have a tutorial. They tell you how they do all their methods. If you just want to run a power analysis, one option you have is to go to another website like NeuroVault, which contains maps from other studies that may have looked at something that you did. Okay, so let's cover that one first. You base your analysis on another study. And by the way, this will all be recorded. So let's say I'm looking at something like self-generated thoughts. There's a past greater than future contrast. Take note, there's Z-maps, T-maps. You can load that into NeuroPower tools. Okay? So you can download it, you can copy the link address, then go to NeuroPower, start your power analysis, and simply just copy and paste that link into the input. It's very clear. It walks you step by step through everything. Right? So we start at start. You copy and paste that URL. You can give it a mask if you want to restrict your analysis to a certain region, for example, for that specific effect. If you were to upload your own data, you just use the upload file. Just upload your own T or Z group map, and then your mask if you have one. Now, you also need to take into account what the design specifications were. You need to know number of subjects, you need to know smoothness, you need to know if there was a Z or a T statistic. So here's the paper that I got that map from. There are Z statistic images. Here was the threshold, 2.3, 14 subjects. I'm really bouncing around here. And then a whole brain extent threshold of 0.05. So if it's not your study, you got to read the paper, just find out what the parameters are that you need to use. And lastly, the resolution is 2 by 2 by 2. Now, once you have all that, am I going to do anything else on this? I forgot if I did. That's the risk of doing this. You know, because I know that it worked, but not totally sure like what the pacing is. Okay. All right, so we have all that. We know that it's Z. We give it a cluster forming threshold, 0.01. 14 subjects. It was a one sample t-test. And then we knew that the smoothness was 8 by 8 by 8, and the voxel size was 2 by 2 by 2. So that's really all there is to it. There are a few things you can look at, but really and we'll walk through a couple of them, but the most important thing is going to be this power calculation. These things, I still don't know how to interpret them, but basically if they look like this, it means that the power analysis is appropriate. Okay, don't know all the math behind it, but they talk about it in the documentation. But the main thing for you, the main thing that you'll be interested in, is seeing these power curves. So if I'm looking at a certain effect and I'm running a study that has about a similar effect, how many subjects would I need to get 80% power? Okay, so these are the power curves. So things like Bonferroni correction, which might be a little too strict, we'll talk about that later. Random field theory is a pretty common cluster correction mechanism, we'll talk about later. So the two main ones probably you might use are things like random field theory or Benjamin-Hogberg. So power, 0.8, how many subjects do I need? Just submit the parameters, press go, and then it thinks for a little bit, and it shows you the intersection between the 80% power and the number of subjects. So for 80% power, 46 subjects. Okay, so we blew through a lot of that, but I just want to bring NeuroPower tools to your attention. It's simple to use. Again, you can use those NeuroVault things if there's a similar study. You can upload your own pilot data if you want to. The one thing I do need to advise you is that lately, if you do upload a sample data set, it wants, I think, at least 10 subjects, or else it won't run. It may be more than you're used to. I'm used to sample sizes of 6 or so for doing a power analysis, but it wants 10 or more. So I'm sorry. Okay, So just to summarize this first lecture, we talked about the physiology of the Bolt signal, all of those assumptions that we talked about. I briefly talked about the basic pre-processing steps. We covered MRI-GL, how to convert raw DICOM images into NIFTI format, and then did a very brief overview of why power is relatively weak in fMRI studies and a few different ways that you can calculate it. Any questions on anything that we've covered so far? All right. Why don't we take a 5-minute break? I need to recover just a little bit, drink some tea. If you need to use the restroom, feel free to do so. When you get back, we're going to give you some instructions for how to log on to the cluster to do the practical. So 5 minutes, so meet back here at 10:25.